Now let's apply this polynomial arithmetic to a mathematical model that will allow us to make the biggest possible box out of a rectangular piece of cardboard that we're starting with. So we begin with a flat piece of cardboard, and originally it measures 40 inches wide, so from here to here 40 inches, and 60 inches long, so from here down to here is 60 inches. Now what happens is you're going to cut equally sized squares out of these four corners, and then once those squares are gone, you're going to make little creases along the little tabs here, fold them upward, and then turn it into a box. Okay? So the only variable in this entire mix is the length of the side of the square that you cut out from step 1 to step 2. So let's let x represent the length of the side of the square that's cut from the corners. What I need to do first is to create a polynomial function that models the box's volume in terms of x. So since this is a box that has a height and a width and a length to it, start with what you know. Volume for a rectangular box is always going to be width times length times height. However, we need to discern ways of describing the width, the length, and the height in terms of the variable x. And again, x represents this little guy right here. X is just the length of the side of the squares that you're cutting out. Okay? So each of those are the same size square, and they should affect the dimensions of the final box to begin with. Well, if you deconstruct the box back this way, here's the length. So if you go back one step prior, the length corresponds to this part that was folded down, or that was folded up, just sort of folded back down. And then here's the original length of the 60-inch piece of cardboard. But what's going on is you have these two little x squares cut out. So since x and x are cut away there, then that means what's left over is the original length of the cardboard, 60 inches, minus the two x's that you cut away for the length of the box. So the length of the well, I guess that's the middle dimension here. The length of the box can be replaced by 60 minus 2x. And you can figure the width by doing the same thing. The width of the box, if you trace back to the original image, originally on the cardboard was the 40-inch width right here. But then you cut these two x's off of either side symmetrically, so that way this part that folds up becomes your width, and that's from the original 40-inch side minus the two x's that you cut away. So we've got the actual width and length of the box in terms of x. We can write the volume as width 40 minus 2x times length 60 minus 2x. Now what's the height going to be? The height of the box, if you trace that back, comes from these two seams right here being folded together when you crease that vertically. Well, that represents the two x's that you remove for the corner of that piece. So the x dimension that you have right there becomes the height when you finally fold those tabs up and make that corner for the height of the final box. So the height is nothing more than the same as the dimension of the x square that you remove away. So the height is just the same as x. So we now have a volume polynomial that's a function of only x. We'll name this function v of x and leave it factored like this. There's no real need to multiply it out. The monomial I'll put to the front. X times 40 minus 2x times 60 minus 2x. And that should be a function that models the volume of this box based on how big of a square x you cut away on the original piece of cardboard. Now, here's a very keen question to come up with the answer for. What is the domain of the function? Now, originally I told you that the domain of a polynomial function is all real numbers. When you're dealing with a generic polynomial that's not used for a mathematical model, that's true. But there are certain values of x that don't make any physical sense here. For example, calling x negative or even calling x 0 won't even allow you to make a box. So I know x is going to have to be greater than 0. Okay, but is there a maximum value of x that you can use? For example, could we cut out little x's that are 10 by 10 inches long? Well, 10 inches here, 10 inches there. That leaves 20 inches for the width of the box. 10 inches here, 10 inches there. That leaves 40 inches for the length of the box. Okay, so yeah, we could still make a box if we cut out 10. What about 20? If you cut out 20-inch sides, well, 20 here and 20 here equals the same as your width. But you can only cut out a square that's as big as, less than halfway across that width. So I can't go as high as 20 for x, because then there wouldn't be anything left but a two-dimensional piece of cardboard that's 40 inches this way, and well, technically 40 inches this way is a square. So I can't cut out, well, actually 20 inches by 40. So I can't cut out little sides that are 20 inches long for the little squares, because that's half the distance of my original width. So at the same time, x needs to be something less than 20, which means the domain here should be open parentheses 0 to 20 close parentheses. So my x is going to live in this set somewhere. I should only cut out squares that are bigger than 0 but less than 20 inches long. Okay. Well, now knowing this will allow you to use your calculator to help figure out a very important thing. How big should our little x squares be in the original cut up here to make this box as big as it possibly can? So I want to sketch a rough graph of the volume function and then use the calculator to estimate the maximum volume that you could actually attain. Well, on this domain, between x equals 0 and x equals 20, that's the only part of the graph we're going to see. So if I were to look at the end behavior of this graph, this is a polynomial of degree 1, 2, 3 with a positive lead coefficient, because negative 2x and negative 2x will be positive. So over here, it'll be going down on the left and be going up on the right. X equals 0 is multiplicity 1, so it goes straight through. And then between here and 20, x equals 20 is my next 0, multiplicity 1. It'd reach a maximum and then come back down to an x-intercept with multiplicity 1. So it probably roughly looks something like this. Between x equals 0 and x equals 20. We don't need to go all the way out to x equals 30 because that's past the domain of the function. So let's look at the calculator to see what our graph could actually look like. So type in your volume function, x times, parentheses, 40 minus 2x times 60 minus 2x. Now, don't do zoom standard here. You've already got a domain cut for this function, so keep in mind this is the domain you want to apply. So what you want to do is on your window screen, oops, there we go. My window is still set to zoom standard. On your window screen, you want to start at x equals 0 for x minimum and let x maximum be the max x you can use in the domain, 20. And you can change the scale to, 5 or 4, whatever you want to. But let me show you a handy feature on the calculator. If you're lucky enough to discern the domain of a function and you can type it into the window for x minimum, x maximum, then the best way to see the graph of this based on that domain is to go to zoom. You got to cursor down a little bit until you see zoom fit. Zoom fit's a really handy feature because what it does when you select it, it'll take the x values in your domain, think a second, and then plot a graph that's based on 0 to 20 domain, but then it'll fit the y values to only the y values you need for that particular domain. So I was pretty close. Mine looks more like a parabola. This one, the maximum occurs a little bit left of the center mark. It's somewhere between, it's not exactly at 10, in other words. It's somewhere a little bit to the left of 10. So that maximum, which represents the maximum volume of this box, let's see where it occurs at. So if I calculate that maximum, second calc, maximum, move my cursor somewhere left of that tallest point, anywhere to the left will do, mark that by hitting enter, move your cursor somewhere to the right of the highest point, mark that by hitting enter, and then it will guess the coordinates of the maximum when I hit enter a third time. So that maximum occurs, it's right up there at the top, at about 7.8 for x and 8450.4 for y. Remember, this x stands for the exact same x as in the picture. This x represents the actual size of the squares. So x should equal, well, I shouldn't say equals, x is approximately about 7.8 inches, and that's for the square cuts. And then the max volume is the output of this function. The y value on my calculator represents the volume output from width times length times height. So the maximum volume that you could get was about 84,050 and then 0.4. Wait, I read that wrong. 8,450.4, excuse me. Now what would the units be here? If x is in inches and you're multiplying height of inches times width of inches times length of inches, inches times inches times inches matches up with the units you should have for volume, which are cubic inches. Okay, so if you go back to your original piece of cardboard and cut out about 7.8 inch squares on the corners that are 7.8 by 7.8 inches in length and width, then fold it up, then it'll give you the biggest box you can possibly have with that cubic capacity inside of it.